In this study, we succeeded for the first time to measure the nuclear spin of single atoms that we put on a surface. The nuclear spin is a tiny magnet inside the core of an atom, and these can usually be measured only in large numbers. As a consequence, we were also able to identify different isotopes atom by atom for two elements in the study, iron and titanium. We could also show that the nuclear spin can act as a sensor to sense, to detect the magnetic, chemical or electronic environment of single atoms and nanostructures. We had to dig through very old articles and books, but it turns out that the physics that scientists used in the 1960s already to describe large amounts of atoms still hold if only one atom is considered. For single atoms on surfaces, the electron spin, which is much easier to measure, has already been studied for 2 decades in our field. But nobody could ever measure the nuclear spin. So it was already a long-standing goal in our field, but only by improving our energy resolution by a factor of 10,000, we were for the first time now able to detect the fingerprint of that nuclear spin. So here we combine 2 powerful methods. One is the scanning tunneling microscope, which enables us to create images of single atoms. It essentially works, consists of a very sharp metal tip that we move across a surface and that can feel the presence of atoms that we put on top, similar like reading Braille. We combine this with a second technique called electron spin resonance, which is similar to an MRI machine in a hospital. And this allows us to sense, to detect indirectly nuclear spins. Our research helps to test current theories for the structure of atoms and materials. Also, to further improve electronic devices, scientists like us have to find smaller units for data storage and develop new concepts for computation. The nuclear spin of single atoms is actually an interesting candidate for both.
Quantum nanoscience is a new research field that combines quantum science and nanoscience. Nanoscience has been around for about 20 years and explores the properties of very small systems going down to the atomic scale. Quantum science nowadays is extremely important because we're striving to achieve quantum computation, a new way to do computation. And quantum nanoscience combines those two together and tries to do quantum computation and other quantum properties of materials on the nanoscopic scale. The ultimate goal of the Center for Quantum Nanoscience is to finally find something that we do not understand. We want to find new experimental results that go beyond the theories that we have to date. That would be a really great breakthrough for all of physics. The Center for Quantum Nanoscience of the Institute for Basic Science here at Iowa Women's University is trying to focus on a subset of quantum nanoscience. In particular, we're looking at the properties of atoms and molecules on surfaces of clean materials. This is really where we are the world leader and where we can really drive the field of quantum nanoscience. The Center for Quantum Nanoscience has a very active international network of collaborations. For example, this work was done in combination with researchers at IBM in the United States of America. We also have active collaborations with research centers in Germany and in France and in Spain, in Europe, but also in China and in Japan. QNS really tries to be an international hub for quantum nanoscience to bring people, researchers here, let them work with us and send our people to international locations.
현재 사용되고 있는 전자소자의 대부분은 물질의 자성을 이용하여 정보를 저장하거나 연산을 처리하는 것입니다. 이번 연구의 성과는 자성의 원리 중에 하나인 원자핵의 스핀을 연구한 것입니다. 물질의 자성에 대해서 보다 깊은 이해를 제시하고 이를 통하여 양자역학적인 효과를 연구하여 스핀 소자의 개발의 가능성을 제시한 것입니다. 스핀이란 양자역학적으로 핵이나 전자가 회전하면서 생기는 자성을 말합니다. 스핀 소자란 자성의 기본 단위인 스핀을 이용하여 디지털 정보를 저장하거나 연산을 하는 소자를 말합니다.